Hi, and welcome to this last seminar from the RE4AFAGRi project on the MESSAGEix Nexus application. After you have probably seen the other two videos on an overview and how to install the model. In this presentation, we will give an extended overview of the model that recalls a lot of what introduced in the previous overview presentation. Then we will focus on the case study within the LIPRI project on Zambia. From a theoretical point of view, the scenarios and results, and then also a hands-on session showing how to run the code that has been installed to basically run those case study scenarios. Finally, also a hands-on session, but also more theoretical on how to develop the model for another country for interested users. As mentioned in other presentations, within the LIPRI project, MESSAGEix Nexus is used as a country model for Zambia, and it's connected to other models to the RE4AFAGRi platform. And we will see first the generic behavior of MESSAGEix Nexus, and then also how it has been applied in this project and connected to the other models. MESSAGEix Nexus can be used to inform policymakers or developers, investors, and especially in high-level policy and long-term time horizon. In particular, it can be used to explore capacity expansion in water infrastructure, agriculture, and energy technologies under different narratives or specific policy scenarios, and also used to assess commodity flows and prices, for instance, of surface or groundwater, electricity, or crop products. And ultimately, the model is also used to have estimates on investment requirements or investment portfolios under these different narratives and scenarios, and which can be also sector-specific and defined with energy expert or agriculture expert that are interested in specific policies, and the model can be used to also understand cross-sectoral implication of such policies. A bit more technically, the model gathers especially in temporally distributed data, for instance, from hydrology, from the ISMI database, or other type of spatial data, also originated from other models like water crop, Emlet, and onset, and it upscales and aggregates these into this MESSAGEix infrastructure planning model, which has a slightly more coarse spatial resolution, and it's on 5-year, 10-year time steps. But in each of these special nodes or special units that are in this case across between basins and provinces, we have a detailed representation of water, energy, and land technologies, demand, and supply options. And after upscaling this data, the model can be run with a long-term horizon time frame, and the output of the model are, for instance, investment trends and investment portfolios. While the model is an optimization model that minimizes total system cost under specific exogenous demand trends or policy constraints. So here is an example of a type of results the model can give, and the model is instructed with historical data, for instance, it's based on electricity generation, but also on demands and technological costs, and also future assumptions, for instance, on sectoral demands, in this case, in the energy sector, technological costs, and capacity factors, efficiency, and so on for the future. But we are trying to find out what would be the electricity generation to meet this demand and other additional constraints which can be policy-driven. And the model kind of provide this solution based on optimizing minimal total system costs. So a cost optimal solution to provide electricity in this case. So one of the main components of the MESSAGEix model structure is technologies. So it's important to understand what we refer to as technologies. Those can be real technologies like cars, reactors, power plants, pipelines, or also something that we usually not refer to as technologies like building, crops, or even river, but basically elements that have inputs and outputs, and maybe have assigned costs, for instance, investments or variable costs. And we often use this example of a coffee machine, which is not a technology message, but is a simple example which has some inputs. We call those commodities. For instance, electricity or coffee powder and water, and some outputs. In this case, is coffee. And some of these commodities can have also different levels, like electricity at the grid level, at the user level, or useful. We often call useful level is basically the demand level. And there might be other technologies before or afterwards in the pipeline. For instance, providing coffee powder. There might be extraction or coffee productions and beans. And also the model often tracks emissions. Can be CO2 emission or waste heat or whatever type of emission. The coffee machine has some costs, investment costs, you need to buy it, and maybe also some maintenance costs. If it breaks, it needs to be repaired, components can be replaced, and also power plants or any other technology in the model might have these costs. They also have a lifetime. The expected duration of these technologies before it's dismissed. And also a capacity factor. So how long in 1 year is the machine run? What are the maintenance breaks and so on. With a full set of technologies, commodities, and for instance, demands are usually expressed in terms of commodities at a specific level, like electricity at a useful level. Then we can map entire systems, like the energy system, but also water or crop systems for the case of the Nexus model. And here is a simple schematic of the supply chain in the energy system, where we have resources, renewable potential, for instance, or fossil fuels. We have primary energy, which get converted and processed by, for instance, power plants. And we have the secondary level, for instance, electricity, that is then transmitted and distributed to the final level, which is then, with other efficiency conversions, the demand level or useful level. And once a complete interconnected set of technologies and commodities and demands is defined, as schematically showed here in the right, where we have different technologies, different demands, and from resources and commodities that provide these commodity flows, then the model is a linear optimization model that minimizes total system costs, basically defined by cost coefficients, a solution vector x, which are different variables, and discount factor. This is in general the objective function of message. And there might be different constraints like demand levels or specific boundaries, limitation of use of technologies, and that can be policy driven. For instance, we want to phase out some technologies that are expressed by additional constraint equations. In this case, we have constraint factors B that affect the solution vector X. But what are these variables that are part of the solution vector X? There are several variables like emissions, but the most important are capacity and activity. And it's important to understand what they are doing and referring to, because they are strictly related to technologies. Capacity is basically the installed capacity of a specific technology that in the energy sector is often expressed in kilowatt or gigawatt of installed capacity, but in other sector can be, for instance, referred to cubic kilometers of water or crop production, like hectares or tons of production for a crop. This can be capacity. Activities is referring to the use of the technology. How much is this technology used? For instance, in energy sector, we think about kilowatt hours. So the amount of energy refers to the activity level of these technologies. And capacity is often related to investment costs. To install your plant or technology, you need to do initial investments that is then discounted for the future years, while activities have fixed and variable costs that every time the technology is used, those costs are basically implied. And these are the costs that are affecting the objective function in the factor CT. So you've seen this slide already in the previous presentation, but here we can describe with more detail. Basically, this is a simple representation of the water system in the model, where we have different water resources such as surface water, seawater, and groundwater, and that there is water distribution system including pumping, distribution, deviation, and also other technologies like desalination. They can provide other types of water. And there are water demands, which are exogenous in terms of urban and rural, or endogenous coming from energy or the land sector. Plus, we also model return flows, especially from the urban and rural municipal and industrial systems, with the possibility to treat wastewater and recycling, so injecting back into the circle. You see also with different colors that we highlight different commodities. In particular, here is electricity use. Here's a similar schematic for the energy system, where we have a set of power plants that generate electricity. And there is also actually the whole resource extraction, especially for fossil power plants. And here you see also commodities that are linked, such as water needed for cooling thermal power plants, and biofuels in terms of for the biomass power plants. And then we have power transmission and distribution lines that connect to the electricity demands, which are exogenous in terms of rural and urban, or coming from the other sector, endogenously water and land sector. And we also model rural off-grid generation, also urban, but it's a small extent. So and this is in this project just as one technology that represent sub-technologies like diesel generator, small PV, or mini grids. And the model also tracks for emissions such as CO2 and other pollutants. Then we have crops that are coming from the water crop model for this project, and there are different irrigation systems that might have be more or less efficient and have different investment costs. And also here there is water use for agriculture and also some pollutants. As mentioned before, the special resolution of NEST for this Zambia application of the LIPRI project has user-defined BCU, which are based in country units, which is a crossing between hydrological basins and country provinces. And the temporal resolution, it's also flexible in this framework, it can be changed, but we use multi-year time steps. There are 10-year time steps, so 2020 to 2030, 40 and 50, but also have the sub-annual dimension of the months from January to December. And also the historical time is up to 2020, and basically development time where the model is finding new solutions is for the time steps after that. A thorough description of the data sources, in particular for the water module, which you can also find on publications, and also where these files are located in the GitHub folder, looking on a data column. And you see water basin boundaries, power plant water use, water availability, as well as water demands, and a lot of data for mapping and defining water infrastructure. Here you see a full list of the possible output of the model, indicators in the energy sector, from energy demand, supply, investment, and installation capacity. In the water sector, like extraction, withdrawals, so demand, investments, and people with access to clean water. Related to land, we have crop water withdrawals, crop yields, crop production, and also more generic socioeconomic indicators, like I mentioned, population with access to water, or access to electricity for cooking, or population at risk of hunger, or food waste, and such things. Here is a link also to the RE4AFAGRi dashboard, where outputs of Nest are also uploaded and can be visualized online with on pre-existing scenarios. If you want to explore more about the model, there is a link to the official documentation of the MESSAGEix model, and also previous papers that have been published with the previous version of Nest and the current version of the MESSAGEix Nexus module. In this section, we talk a bit about the actual case study we ran for Zambia, with a focus on rural renewable electrification and the linkage with agriculture in rural areas. So hopefully this will help you also familiarize with the model behavior and how it could be used also in other applications. For this application, we define some scenarios, which means some narratives for future years, and each of these narratives corresponds on different way of parameterizing the model. So, for instance, establishing exogenous demands or constraints that are in line with the scenario assumptions. And here we have first a baseline scenario, or also called a business as usual. So a scenario that represents current policy, current trends, and growth, for instance, in electricity demand, and also say current assumptions in agriculture land use. A second and more ambitious scenario is called improve access. Here we target some goals related to, for instance, the sustainable development goals. In particular, concerning electricity access, which is still low in Zambia, we have the target to halve the gap, so the number of people that don't have access, to halve it by 2030, both in the rural and urban situations. Similar goals for water access and sanitation, because also there the access rate is still not so high, so we have this gap by 2030. And there is also a food security policy, which is increasing water supplies to meet domestic food crop production demands in 2030, keeping the diets similar to current diets. Then there is an even more ambitious scenario called ambitious development, in which we target universal or almost 100% access to electricity, clean water, and sanitation. And also we have a nutrition security target, in which not only the internal production is going to meet food demand, but also the diet standards for population is increased to the EAT Lancet diet standards. In addition, it's also a sustainable target because we constrain the energy system to be 100% renewables. This is not too ambitious in Zambia, because Zambia has already almost 80% of electricity production from hydropower, but there is also coal mines in Zambia, so that could be a suitable solution, but in this scenario, coal is basically banned. On the right side, you see a plot showing the electricity demand as an output from the MLED model for different sectors, crop processing, industrial and residential and commercial demands, and you see how these are defined for the different scenarios, with the ambitious development scenario having the highest demand level. We also collected data on connection to clean water, so access to clean water and sanitation for urban and rural areas in Zambia. And you also see here the different trends of basically access to clean water versus on the left panel to rural areas, that in the baseline scenario it would not get to 100%, if not by 2070. So in 2050 it would be still below 90%, while the other two scenarios have a stronger increase in water access, in basically population with access to water by 2030, reaching 100% for ambitious scenarios, or reaching it by 2040, basically with the improved scenario. Here we also have the implications on the land sector. This is a map of Zambia. On the left side, showing for different time steps, so 2020, 2030, and 2050, and for different scenarios, baseline, improved, and ambitious, how crop basically water withdraws. And on the right side, is also water withdrawals, but by crop instead of by region, how it changes to meet the goals set for these different scenarios. And this is outcomes from the water crop model, but this becomes also an input into MESSAGEix Nexus. As mentioned also in the overview presentation, we developed these 3 main scenarios for this particular project, but basically the model is designed to be able to design many other different scenarios that any user or stakeholder can indicate. For instance, development pathways, as we did, or implementing climate impacts, like there are impacts, for instance, affecting the power plant system, water availability, precipitation, or crop yields. And we can test these different climate impacts, basically running different climate scenarios. Or also other environmental policies, as we did in previous paper, like ecosystem preservation or maintaining a minimum river flow in the river streams, or also exploring different food exporting or importing policies and targets can be also an option implemented in the model. Here you see just an examples of combining outputs from the onset and MLED models, input into Nest. In this case, we have different scenarios with different increased access of electricity, and we see different use of electrification and off-grid technologies. And we use Nest to see what we're going to be the energy generation mix for a specific scenario, and comparing different scenarios to estimate basically expected increase in average investments in different sectors. And similarly also for the water sector, where in water we will have different demands, municipal, industrial, or from agriculture, and different supply possibilities and different expenditure for according to the level of development, water access, or use of irrigation technologies, for instance, that we set in different scenarios. And in this case, we set specific scenarios that are very ambitious on agriculture use and see very high increase in cost in agriculture and irrigation. Okay, now I assume you have cloned the RE4AFAGRi repository using the git recursive command you saw in the installation video. And under the GitHub or wherever you downloaded or clone the repository, you will have then the repository here, RE4AFAGRi platform. Inside we see the Nest folder, MESSAGEix models, which is a clone of the official MESSAGEix models with some little changes dedicated to the project and the Zambia project. So let's look what we have in this folder that is relevant for the purpose of replicating the project, the scenarios we run for the LIPRI. Now I suppose you have cloned the RE4AFAGRi repository from the Okay, now we see how to basically run the scenarios we developed for the LIPRI project for the country model of Zambia. And I suppose you have cloned the RE4AFAGRi repository using the git recursive command that you saw in the installation video. And you should have in your GitHub folder or wherever you cloned it, this RE4AFAGRi platform as a folder in your machine. And here you see the different models, and we look at Nest and MESSAGEix models. And this is very similar to what you also see on the official MESSAGEix model repository, but here there are some particular folders dedicated to this project. In particular, within this folder we have data, and there is, for instance, data for the water module, but here we look at the data of the project LIPRI Nest, and there is, for instance, data coming from other models in the platform, like from MLED, costs coming from onset, and there are crops data coming from the water crop model, and these are basically input data for running the scenarios. For instance, here are also the name of scenarios: ambitious, baseline, improved. Well, if we go back some folders. There is the code of the model is actually not in the data folder, but within project and library nest. And these are the main scripts we're going to run. Basically, this build script is compiling different parts that we need to generate this model, and it's calling some of the other scripts that are present in this script folder. For instance, a script that adds the grid share generations coming from the onset data, adds electricity demand coming from the MLIT model, and other particular features that you can open and look at it. Then there is other scripts that we are not running here. These are pre-processing scripts. These are basically scripts that elaborate raw data and process it in a format that can be used in the model, and basically is the format that you saw in the previous folder, in the data folder. Okay, but we're gonna go back to using the raw data mostly in the process of generating a model for a new country. In this case, we want to basically go through the process that generates the model and scenarios we use for the library projects for the Zambia model. So back in the library nest folder, there is this Jupyter notebook that has been done specifically for this purpose, for this tutorial. The best way to run it is to open a common prompt or Anaconda prompt. Make sure you open your environment. In this case, message environment, I activate it. And you can locate in the folder you are by doing CD and copying the path. And then you can open a Jupyter notebook, which should open in your browser. In this case, I have another window. So basically, it opened it on another desktop. And here you can open this build file that we're talking about. And this is the process that basically generates a country model for Zambia and loads the scenarios that we required step by step. What this script is doing is basically summarized in this slide. There is a first step where a country model, energy system model has been generated and downscaling the global model, and for this there are some tools that has been used which are unfortunately not yet open source. So in case you want to do it, you will see in the next session. You can contact some of us in the team privately and we can help you doing it for another countries. But in this case, we start basically from step 2, where we have a defined scenario of a MESSAGEix Zambia model, and we add features related to adding sub-nodes. So instead of having one country, we have regions, sub-regions, adding regional electricity demand coming from the MLIT model for the future time steps, and adding information from the onset model in terms of grid and off-grid generation of electricity supply, and also cost of technologies. Finally, in step 4, we add Nexus module, which basically adds the water system and some crop components to the model, linking to the energy system as well. So energy needed for water is here connected, as well water required in the energy system, for instance, of cooling power plant, is implemented in this module. Finally, on step 5, which is also specifically implemented for the library project, we include crops, land inputs, linking from the outputs of water crop model. And in this case, basically we connect crop to the water system in terms of water requirements for irrigation and also energy needs. And these slides also show the kind of specific scenario names that you will refine and recall also in the script that change the names during all the steps. So we run through the script now, running by Shift Enter or Control Enter. And the first part is just loading the packages. And we see that the run is successful when we see number 1 here in the corner. And you might also see some warnings in red, but these are not errors, so you don't have to be worried. As long as here you see number 1, it means this block has been run. We can move to the second block. We can then move to the second block, which is basically opening the modeling platform and defining some scenario names and adding some units that are going to be needed in the next steps. And when it's solved, when it's finished, we can move to the next block. And running this block might be required again in case you, and I will see it in the step 5, in case you have closed the Twitter notebook for some reasons. Now you see number 2 here. We can run the third block. Here is also more technical things. We are basically in the scenario from the existing, and from an Excel file we are loading a scenario that was basically the country model of Zambia, and on it, meaning with another scenario that is called the X name with subs, because in this block some specific subunits are added. The initial model has yearly time steps, and here we add dimension using some specific function, and also we add the sub-region. There's a set node, and we're going to add sub-nodes to it. And also adding the times done in this with specific functions that has been defined for this, like duration time setup and duration time. When this block is also run, we see some outputs here, some warnings. We can also check the scenario names and see if our scenario has been created. This is basically looking into our local data frame. We see a lot of scenarios with model name, and I think this should be one of the last subunits model. And we can also move into the next step, which is demand processing. And you will see also here are some warnings, but these are not errors. This process works and means. To understand what's going on in this phase, you see here that we are looping already for different scenarios. We are creating this particular different scenario setup that we have in the project, baseline, improved, and ambitious development. And this name is assigned to specific scenario names within the model MESSAGEix framework. And we are cloning the previous one into new different scenarios that then will have different instances because we apply functions that are scenario specific. These functions in particular, you can open them and look in detail what they're doing. For instance, here I'm opening the actual function scripts. From the mlet demand, there are different subfunctions, loading the demands from CSV, and restructure basically in a format that is message compatible. So where we define the level, the commodity, and then the of this function is basically loading it into the model. @c is basically name of the scenario, and we're adding set and parameter scenario specific. The add grid shares onset is a bit of function and more complicated. Basically is adding transmission and distribution lines for the basins, having urban and rural differences. And these are basically technologies with inputs and outputs, take electricity from certain levels and output it in another level. In this case, there is also a careful mapping of the basins because the major electricity system in the model is represented in one country only, so has been downscaled. And for instance, hydropower and grid generation is represented just in one region, one node, which is Zambia, while off-grid, rural and urban generation is implemented at the basin level. And therefore the transmission lines and grid connects from this basin supply back to a central node, and then electricity is distributed to meet the regional basin demands. Another part of this function is adding off-grid generation based on outputs from the onset model, which establish which are the optimal shares of off-grid generation, having defined basically electricity price levels for specific years. And also we are adding basically the the technology themselves that provide off-grid generation, which costs, investment cost is also evaluated as an average of the technologies that are coming from onset. So here we lower a bit the detail from different off-grid technologies like mini-grid, solar, and so we make the average, weighted average of the investment and variable cost, and we assign it to just one generic off-grid technologies for urban or rural generation in Nest.